Right, sir. Good morning, everyone. Today I, Rudraneel, will briefly shed some light on the topic space telescopes. So, space telescopes, as the name suggests, are telescopes based in space to observe the distant planets, galaxies, and other astronomical objects. So, if you think about it, is there any need for space telescopes? Observatories on Earth are cheaper than telescopes in space. For example, a cutting-edge observatory on Earth costs around 1 billion US dollars, whereas the James Webb, uh, the most recent space telescope which is yet to be launched, will cost around 10 billion US dollars. And also considering the fact that ground-based observatories are catching up rapidly. The European Extreme Large Telescope, which starts its observation in around 9 years, will give photos 16 times sharper than images taken by the Hubble Space Telescope. So it seems really hard to justify investment in space telescopes, considering uh, ground-based telescopes have caught up to space telescopes. But groundbreaking discoveries made by the Hubble Space Telescope have taught us how valuable they are. So, what is the need of space telescopes? While our atmosphere it blocks off UV rays, it lets through visible light, which is to which our eyes are sensitive. It absorbs light at other wavelengths, so we can never see it from the ground. Addition to it, turbulent motion in the atmosphere blurs the light traveling through it, causing objects to twinkle and appear fuzzy. That's why stars twinkle. Another problem that the ground-based telescope has is they are subject to local weather conditions, and high clouds can ruin the chances of making any useful observation. So, so space-based telescopes eliminates all of these factors, which is why space-based telescopes have uh, upper upper hand regarding observations. So here are some major space-based telescopes. Uh, so first of all, there is the Hubble Space Telescope. I mean, everybody knows about it. Since its launch in 1990, the Hubble has changed our fundamental understanding of the universe. The granddaddy of space telescopes, Hubble, the first of NASA's great observatories, has revolutionized astronomy, providing stunning images of countless cosmic objects. So, the second one is the Chandra X-ray Observatory. The third of NASA's great four observatories, Chandra is the world's most powerful X-ray based space telescope. Chandra is named after the Nobel laureate Indian American physicist Subramaniam Chandrasekhar. The third is the Spitzer Space Telescope. It's also one of NASA's four great observatories, but it's retired now. Uh, the, the Spitzer Space Telescope, launched in 2003, was NASA's infrared great observatory. Among many other accomplishments in its 16 years of operation, Spitzer discovered a giant ring of Saturn, revealed a system of seven Earth-sized planets around a star which is very nearby, around 40 light years away, and studied and studied most distant known galaxies and supermassive black holes among them. Next is the Kepler mission, NASA's most recent mission, NASA's planet hunting. No, it's not NASA's most recent mission. I'm sorry. NASA's planet hunting telescope that specifically searches for Earth-like planets in the galaxy. Next is the Planck Observatory, which concentrates on microwave light of the universe. Planck will be looking at the remnants of the first light to shine freely in the universe, mostly the cosmic microwave background. And here we see some of the space telescopes and the wavelengths they operate in. First is the SWIFT. It's a NASA-based space observatory which focuses on gamma ray bursts. Next, this is the RXTE or Rossi X-ray Timing Explorer. It focuses on X-rays primarily, and Hubble Space Telescope. We all know about the Hubble, NASA's most successful space telescope. This is the James Webb Space Telescope. It's set to be launched in December. It cost NASA around $10 billion to make it. This is the Wilkinson Microwave Anisotropy Probe. It's a decommissionized probe. It is used to focus on microwave readings. So now I'm going to talk about the Hubble Space Telescope. So the Hubble Space Telescope is a space telescope that was launched into low Earth orbit in 1990. and it's still in operation. It was not the first space telescope, but is one of the most largest and most versatile, renowned both as a vital research tool and a public relation boon for astronomy. The Hubble Space Telescope is named after the American astronomer Edwin Hubble, and is one of the NASA's great observatories. Along with Compton Gamma Ray Observatory, the Chandrasekhar X-ray Observatory, and the Spitzer, they make up the four great NASA observatories. The launch date is April 4th, 1990. It focuses mainly on ultraviolet and visible light, even though it sometimes takes infrared readings. Its primary target is deep space, and it's still active. Uh, Hubble features this is the photo of the Hubble Space Telescope. It features a 2.4 meter mirror, and its diameter of the mirror, and its five main instruments observe in the ultraviolet, visible, and near infrared regions of the electromagnetic spectrum. Some Hubble facts. No. Some Hubble facts are Hubble travels at the speed of 17,500 miles per hour and has covered a distance equivalent to a trip to Neptune, the furthermost planet in our solar system. Hubble has peered back into the very distant past, to locations more than 13.4 billion light years from Earth. Uh, since Hubble has been launched in 1990, Hubble has made more than 1.3 million observations, which is quite impressive. So here are some of the notable discoveries of Hubble. Hubble helped pin down the age of the universe, now known to be 13.8 billion. Discovered two moons of Pluto, Nix and Hydra, around 2005. Helped determine the rate at which the universe is expanding. Discovered that nearly every major galaxy is anchored by a black hole in the center, and created a 3D map of the dark matter. We all know this photo is the Eagle Nebula. Hubble had also taken this photo in 1995, which was later named as the Pillars of Creation. Next, we have the Spitzer Space Telescope. It's a it's a retired space telescope. It retired on 20th Jan 2020. It focuses mainly on infrared region of the spectrum. Its primary targets are distant and nearby objects. Now we look at some of the discoveries made by this telescope. Here is the space telescope. This is the sun. This part shields the telescope from the sun, and it's very cold out here, around minus 270 Kelvin. Here are some notable discoveries among the multiple discoveries made by the telescope. It showed us the Saturn's ring, which is hidden in the visible light spectrum. In 2010, researchers used Spitzer to look at some of the farthest, earliest supermassive black holes in the galaxy. They found that for a couple of systems they studied, there was almost no dust in the galaxy centers, which is unusual. The lack of dust meant that they had spotted supermassive black holes in the very early universe, which there weren't many heavy elements for dust particles to form. This helps us understand how black holes and galaxies grow and evolve. In 2016, Spitzer also discovered a planetary system with 7 small rocky planets orbiting a dwarf star. It was also found out at least three of the dwarf planets orbiting the dwarf star was inside the habitable zone where liquid water exists. So one of the greatest discoveries the Spitzer Space Telescope made is the Phoebe Ring. In February 2009, the Spitzer Space Telescope pointed at Saturn and then discovered a huge ring associated with the distant irregular satellite of the planet Saturn, Phoebe. Phoebe at 107 km across is Phoebe at 107 km across is likely a captured body which was drifting through space and got caught by the gravitational pull of Saturn. The satellite Phoebe has a retrograde orbit around Saturn, means it revolves opposite to the orbit of Saturn. Material blasted off Phoebe by impacts of smaller bodies remain in Phoebe's neighborhood of billions of years, which mostly form the ring. That's why it's called the Phoebe Ring. It's pretty huge, the Phoebe Ring. It dwarfs Saturn's size and it makes it look like a small dot. Here is the image of Phoebe's ring if we compare it to Saturn. Next, we are going to speak about the James Webb Telescope, the most recent telescope, which will be launched on December 18th, 2021. It focuses. It's a infrared-based space telescope, means it's very cold. It's yet to launch, and it's also called the successor to the Hubble, and it's considered to be and hopefully it will be the most successful telescope sent to space yet. Here is a photo of the James Webb Space Telescope. This is the mirror of which light reflects, and this is the sun shield, which will shield the telescope from the sun. So the James Webb is so if we compare the James Webb and Hubble, the James Webb is not a replacement for Hubble. Its capabilities are not identical. James Webb looks at the universe at the infrared region, while Hubble studies it primarily at optical and ultraviolet region. Even though Hubble can look into the infrared region, it is not meant to do that. Webb has also a much bigger mirror than Hubble. The large light collecting area means that Webb can peer farther back into space, farther back into time. And Hubble is capable of doing. Hubble is a close orbit. While Hubble orbits the sun around at 570 kilometers, Webb will be at 1.5 million kilometers, which basically means that it is not designed to be serviced by the space shuttle. Unlike Hubble has been serviced around 5 times, the latest one being in 2009. Because Hubble is in Earth's orbit, it was we were able to launch it by a space shuttle. But James Webb will be launched by a raw rocket because it won't be in Earth's orbit. Therefore, it will be launched by a rocket. Yeah. So here's the mirror comparison with Hubble. So Webb will have an approximately 6.5 meter diameter primary mirror, which will give it a significantly larger collecting area than the mirrors available on the current generation, notably Hubble. Hubble has a 2.4 diameter mirror and collecting area of 4.5 meters square, giving James Webb more collecting area and hence better resolution. So we can expect to look much further back in time compared to Hubble. So if you ask the question, how far back can the James Webb Telescope see? So if you think about it in this way, if Hubble can see toddler galaxies, James Webb can see baby galaxies. One reason the James Webb will be able to see first galaxies is because it's an infrared telescope. The universe is expanding. So when we talk about distant objects, Einstein's general relativity comes into play. It tells that the expansion of the universe means that the space between objects actually stretches, causing objects, galaxies to move further away from each other. Furthermore, any light in this space will also stretch. Therefore, they can make distant objects very dim, invisible at visible wavelength of light, because light reaches out at infrared light. Therefore, infrared telescopes like James Webb are ideal for observing these early galaxies. So that's all I'm going to talk about today. Thank you.
Okay, thank you, Rudra. Do any of the students have any questions?
Ajit, you can ask question. No questions?
Okay, no one seems to have questions. Prajosa, you want to ask?
Yes, sir. Rudraneel, it was a very nice presentation. We like the way that you have put in the slides. I do not have any question, but I just want to give a fact that this Hubble telescope was, very. It was a long dream for the physicists, those who are working in astronomy, to get it into, and commissioned into the space to get a deeper meaning into the observations of the space. So finally, they managed. They had a contract with Perkin Elmer, who were interested to design the optics part. So they were basically interested to get this mirror, the primary mirror that you were talking about, get it polished. Okay, so the polishing was done to in order to account for the losses, that the imperfections that in ordinary mirror that we see. But later on, once it was installed into the orbit, the on the observation part, they found that there was the image that they have been receiving is not that well resolved, okay, as they had expected. And it was because of a small flaw that led to this huge problem, and it incurred a lot of loss to the government as well as to the funding agencies. And later on, I think they solved this by installing some other uh, additional gadget into the telescope and sacrificing one of the instrument installed therein. So they had a pretty tough time, Perkin Elmer and NASA, and then later on Kodak also intercepted to give their contribution to the design of the mirror. But ultimately, it is the Perkin Elmer mirror which has been installed in the Hubble Space Telescope. That was one of the facts I knew, and that is it. Thank you.
Thank you, sir. Yes, sir. So I think so around 1993 there was the first means the first photos taken by Hubble were quite
Uh,
blurry.
they had to do back calculation by using the errors that crept in the images, and they had to find what was the exact error, and it was because of the polishing that they didn't went into the exact described amount, and because of that there was this aberration thing, and the images were captured were not up to the at par with the expectations.
Thank you, sir.
Digvijay sir, any questions?
I also don't have much questions. Anyways, is there any specific reason why the mirrors were shaped hexagonally in James Webb telescope?
No, sir, not that I know of. I can't answer this at the moment.
I don't actually know why they did it specifically for the James Webb, but we also used a hexagonal structure, not for mirrors, but for the detectors, because hexagonal panels are easier to construct up to specifications and easier to transport without causing any sort of injury, because they can be stacked and kept in very stable stacking positions. So that was one of the reasons why we had chosen it. They might have used the same, because those are very delicate mirrors, no? So it needs to be transported and things. Maybe they decided on that structure. And you can easily honeycomb a mirror of any size you want because of the hexagonal stacking.
Okay, thank you, sir.
But I don't know if that's the exact reason the James Webb guys used. But hexagonal structures is used quite a lot in detectors and telescopes.
Yes, I think it gives you the flexibility to design the macroscopic shape of the mirror, any type of shape.
Yeah,
And also I think it will provide the structural support also, this hexagonal shape.
Yeah, because the thing is, once you make a circular mirror, you're stuck with the mirror. You can't make it bigger or smaller, and you can't
Correct.
the mirrors together. But hexagon, you can always, make it as big as you want by just adding more and more on the sides.
Okay. And yeah, I'm not familiar how probing the infrared region you can basically probe like more further in the past? I mean, I'm not familiar with this.
So infrared light coming from most of the lights, it gets absorbed or like it doesn't reach our Earth. So infrared light, since it has long waves, so it reaches almost to us.
I mean, like, why specifically infrared? I mean, was my concern.
Why specifically infrared reaches us? So I mean, so that's all I know, sir. Because infrared has long waves, long wavelength, more than visible at least.
Okay. Maybe Vikram sir can expand.
I don't know why, but Rudra should know why we're using infrared. Okay, at least tell us why we are not using telescopes on Earth to study infrared.
So because Earth's telescopes, like UV lights, they get deflected by the ozone layer. Other lights, they get absorbed. Hence,
Yeah, there's atmospheric absorption in infrared. That's correct. Yeah.
Okay, sir. That's all from my side.
All right, JWST, biggest astronomical event that's going to happen this year, unless it gets delayed. By the way, JWST was originally supposed to be launched in 2007. So it's been delayed by 13 years so far, 14 years, and it's probably going to be delayed. And some people think the telescope is cursed because every time they signify a launch date, it always gets delayed. It was supposed to get launched in 2007, then 2011, then 2015, 2016, 2018, then COVID happened, and then it was supposed to be launched at the end of this month, and now it's been shifted to December. So it might never get launched at this rate. So Rudra, good presentation. You did your background look at all of the telescopes, what they do, and all of that. I do, however, have two questions. First of all, why is there no thank you slide at the end, and where is your reference slide?
so the first thing is, so I have a thank you slide. It didn't just show. I don't know why.
Okay, well, where's your reference slide then?
Yes, sir, I forgot to do that.
You
I
forgot.
realized it while
You need to tell people where you get information from. It's very important. See, this presentation is, like I said before, immaterial. It's just practice. But when you actually do presentations, there is a certain formality that you need to. There's a certain format of presentation that people will expect, and the reference slide is always there. Right? Like the thing is, if your reference slides aren't like if you don't make your references exactly like EMS and all that, it's not that huge a deal. We still know where you're getting a reference from. We can see the Wikipedia pages, but this is expected from a science student. That's why I'm like, yeah, make a reference slide, make it like EMS format and all that. This is so that later onwards you guys know that this is what's meant to be done. So reference slide. Okay, so the reason James Webb is looking at infrared is it is looking very, very far back. The further away you're looking in the universe, the further back in the history of the universe you're looking. Because the further away you look, when light is traveling, light takes time to travel. So the further we look into the universe, the further back into the past we're looking at, because we're looking at light rays that were sent in the past. The problem is the universe is also expanding with time. So these light rays that have been emitted from these galaxies, these very energetic light rays that were either X-rays or gamma rays, because the universe has been expanding, the wavelength of the light rays has been stretching out. And over all of those billions of years that they've been traveling to us, they've been stretching out from X-rays down into ultraviolet, down into all the way to infrared. And that's why the JWST has to be an infrared telescope. Because the sorry, sir?
Sir, please continue, sir.
Yeah, so the light rays that we are studying, because it wants to study really, really distant galaxies, those galaxies, the light rays that came from, the photons that came from those galaxies have now been stretched into the infrared and maybe even the microwave region.
So depending upon what object you want to probe into space, so depending upon that, you try to make a telescope that would sense the type of electromagnetic radiation, right?
Depending on the type of object and how far away.
How far? Correct.
Both of these will be interconnected.
And I think that is the reason why
the Chandra extra observatory was an X-ray detection observatory, and it did quite well. It could probe pretty far back, but there was like an upper limit. how far it could see, because no matter how, unless the event was super energetic, anything the galaxy is going to give out, it was going to be like lower than X-ray.
Correct. And that is the fundamental reason why the mirrors have to be as sensitive as possible. So this polishing means that we are actually decreasing the surface roughness, no sir? This crest and trough that really appears on the microscopic level, we are trying to bring it down.
Yeah, because a smallest amount of aberration will cause interference, and that will cause all sorts of issues. Because again, the signals are fairly small. The amplitude of the signal is fairly small. It's one of the reasons also why the cosmic microwave background is microwave, because they were extremely energetic rays, but over 13 billion years they're stretched out into microwaves. So that's the thing. Rudra, you said that the JWST is at a Lagrange point, right? Did you specify that?
Yes, sir.
Can you explain what a Lagrange point is?
So, it's like, I saw a picture of it. I can just tell you that it's like if you draw a straight line from the sun to the earth.
Yeah, but why do we care about Lagrange points? Why is it so important to keep a telescope there? Because a Lagrange point for us is, as you have shown in the diagram, it is further than the moon. Like if anything happens to a telescope, it's done. A micrometeorite impacts the mirror and just shatters it, like it's done. We can never repair the telescope. You can never send someone out there to repair it. That's one of the reasons why there's so many delays. They have to make sure everything's perfect. So why are we putting so much effort into sending it all the way to a Lagrange point? What's important about Lagrange points?
So I didn't think about it this way, so I can't answer. Maybe we kept it in the Lagrange point so that to shield from the sun's rays.
Okay. So I don't think Lagrange points are in the undergraduate syllabus, and I think they should be. But so when you have two bodies exerting gravitational force on each other, and we're talking about two bodies of different masses. So there's one body that will have more of a gravitational effect than the other, depending on the masses of the two bodies and the distance you're looking at, right? But at certain points, the gravitational force from both these bodies will perfectly balance each other out. Okay? For the Earth-Sun system, there are 5 points called the 5 Lagrange points, where the gravitational forces basically cancel each other out. The L2 is the second Lagrange point. It is a point of extreme stability. All right, and that's why we put satellites there, or we are putting the telescope there. The L2 point also is already housed to quite a few satellites. They just stay there and they're extremely stable. If there's any sort of gravitational disturbance, it might oscillate a bit, but it will always come back to a Lagrange point.
All right.
Okay, does it make sense? Also, it's quite far away from the Earth, so there's no, like, it's kind of it's a very isolated region in space. So local disturbances won't affect the JWST. So it doesn't have to deal with the infrared emanating from the Earth's atmosphere, for example, or from the moon. Both the Earth and the moon will also be emitting infrared radiation because they're reflecting light from the sun, especially the Earth because it absorbs radiation from the sun, and in the nighttime it sort of emits the radiation as infrared. It won't affect the JWST. Okay.
That's all. Thank you.
Yeah. If you want to, if for anybody who's interested in Lagrange points, there is a group of asteroids called the Trojan asteroids in the orbit of Jupiter. They're in the L4 and L5 Lagrange points of Jupiter, and they're also in extremely stable orbits around Jupiter. Yeah, I don't really have any other questions. It was pretty good. Your preparation was good, but again, I think the small little your slides, you needed to have some more slides about the end and a little bit of detail about what the Lagrange point and why some of the construction stuff. I think you could have gone into a little bit more detail.
I'll keep that in mind next time, sir.
Okay.
Thank you, sir.
Okay.
Rudra.
Yes, sir.
Sir, may I interrupt?
Yeah, please go ahead, sir.
Can you tell why these satellites that we send into space and orbit around the Earth, like why they are covered with a gold or a silver foil? we have seen, no, in most of the cases, at
Yes,
least,
even the James Webb is covered.
if
gold.
not, yeah, if not physically, at least in movies or videos we have seen. Is there a reason, or just for a show that they have?
Via like the mirrors or the whole satellite, sir?
The satellite is covered, no?
The mirrors are covered with gold, kind of a gold foil. The satellite is covered with a silvery foil, an aluminum colored foil.
To like to shield the satellite from radiation from the sun.
Sure.
He is correct. Yeah.
Yeah, also to minimize, I think, thermal fluctuations, no? Because
Yes.
yeah, once the radiation is the only mean to exchange of heat energy with space, in space. So in order to control the thermal fluctuations, ultimately again have impact on the electronic components installed on the device. Yes, yes. And
Yeah.
sir, why are the mirrors covered in gold?
Sir, to optimize, sir. So the mirrors are covered in gold to so optimize.
Optimize what? What is being optimized?
So the like rings and
Acha. No, gold mirrors are covered by gold foil, means it is covered on the top, or it is at the background or something like that.
so only on the
I
top.
think so I don't remember exactly. Rudra may know this. Is it just the top or is it all around?
So only on the top, sir.
Only on the top. Gold is very reflective. Also, is fairly difficult to sort of. Gold won't flake off. So if it has like impacts from micrometeorites or something, it will affect the smoothness of the mirror, but it'll still be able to reflect something.
Acha, acha, acha.
So interference. So if it reflects and dents the gold, it'll cause interference errors, but you can correct that mathematically. Or you can account for it. But if the mirror flakes off, then that's data you're never going to get. So that I don't know if what exactly the logic is behind GWST, but some of the telescopes also use gold plating.
Acha, acha, acha. Okay, sir. Thank you. Thank you, Rudra.
Thank you, sir.
And the foil that is used, it's either Kapton or Mylar. I think JWST uses Kapton. And like Rudra said, it's to shield. It's to provide a reflective shield from the sun's rays. If you have seen like fire reflecting suits that firemen sometimes wear, it's also used for similar. And if you stack the Kapton films together and you keep it in vacuum, it basically serves as a radiation insulation. So it also prevents any heat from the JWSTs leaking out into the outside.
Acha, acha, acha.
We had to use the same setup for our thing also.
So we are very privileged to have one of the faculties who really work on this telescope.
No, I didn't work on the JWST.
But anyway, yeah, you have
smart enough
connections
to be
in
part
some
of
way.
that.
Yeah.
But the telescope that we worked on had to use some of the ideas that are also used in a lot of space telescopes. So, the Mylar film, for example, is it's cool, but it's a real pain to work with in real life. I don't have fond memories of it. Okay, thank you so much. Okay, does anybody else have follow-up questions? Okay, Rudra, thank you so much for your presentation.